All right, so this is a little wrap up on the introductory questions that you answered on the first day of this unit. So I just have the Google Sheet up of some of the responses. Not all of them are in yet because not everyone has had class, but this is kind of give you a good idea. Okay, so number one, when a battery no longer works, it is out of charge and must be recharged before it can be used again. Okay, most people answered true, but we know now that it is false. We'll talk about that in a minute. Okay, number two, the charge that moves through the circuit originates in the battery. Again, but hopefully before the lab, most people thought this was true. Hopefully now everybody knows that this is false. Okay, number three, charge becomes used up as it flows through the circuit. The amount of charge that exits a light bulb is less than the amount of charge that enters it. This one, surprisingly, is also false, but more people answered false than true, so that's a good sign. Number four, charge flows through circuits at very high speeds. This explains why the light bulb turns on immediately after the wall switch is flipped. Most people thought that was true. Again, this one is false. Okay, and number five, the local electrical utility company supplies millions and millions of electrons to our homes every day. Again, most people thought this was true, but this is also indeed false. Okay, so these are all false. So let's take a look at these. One by one. So when the battery no longer works, it's out of charge and must be recharged before it can be used again. That is false. All right. Remember, the charge exists everywhere in the circuit already, and the battery's job is just to pump the charge, not to create it. Okay. The charge already exists. Okay. The charge that moves through the circuit originates in the battery, right? Again, false. Same thing. The charge already exists in all of the objects. It's just the electrons in the atoms that make up everything. That is not created anywhere. It just is. The battery supplies the pumping action, does not supply the charges. Okay. Charge becomes used up as it flows through the circuit. The amount of charge that exits a light bulb is less than the amount that enters a light bulb. Okay. Again, this is false. The charge is already there. It's there anyway. It stays there. It just moves around. All right. What you might be thinking of is something is sort of quote unquote used up as it goes through the light bulb. What is the thing that is kind of used up, right? It's the energy, right? So the battery is sort of supplying energy to those charges, and they are moving around. Oh, I got a graphic I want to show. And when the bulb creates light, that's the energy being transferred to the light bulb. Okay, so the energy is sort of exiting the system, shall we say, in the form of light. Okay, but the charges are still there. Okay, charge flows through the circuits at very high speeds. This explains why the light bulb turns on immediately after the switch is flipped. Okay, again, false. Actually, charge flows very slowly, super slowly actually, and the light bulb comes on immediately because the charge is already there. It just receives the signal to go. Okay. And then the local electrical utility company supplies millions and millions of electrons to our homes every day. Again, false. The electrons already exist everywhere. The company just supplies the pumping action to make them move. All right. So I'm going to pause this because I've just thought of some graphics I wanted to show you. Okay, so there's a couple more things that you should have read in the hyperdoc. I think if you did not do the hyperdoc already, you should probably do that first and then come back and watch this. Okay. The analogy between gravitational potential energy and electric potential energy is detailed in the readings from physics classroom, and it's kind of confusing, but the main thing that you want to understand, right, is that the battery works kind of like gravity does, right? So you have a high gravitational potential energy location and a low one, right? So given nothing else happening, if you put something like a rock at a high potential energy location, like above the ground, and just let it go, it will fall down to the lower potential energy location, okay? If you want to go the other way to raise it from low to high, you have to put in work. You have to do work from an external force to lift that rock to the higher location so that then it can fall back around, okay? So that's basically what's happening in the battery here, right? So the charges are moving around the circuit, okay? And you saw in one of the readings that we're going to even though it's actually electrons that are moving, we're talking about it as being the positive charges that are moving, even though it's not really correct. And everybody's known this for hundreds of years, but we decide still not to make a change, okay? So we're thinking about it as being the positive charges that move from the positive side of the battery back around to the negative side, okay? So this is almost like being high above the ground and here being low above the ground, right? So those charges start at a high place and then they fall and move around to the low place. All right. In order to go from low to high through the battery, work has to be done, right? Something has to happen to move those against the way that they want to go. All right. And that's the battery's job, is through this chemical reaction to supply the energy or the work to drag this charge from the low place to the high place. And then it kind of falls around the circuit. The battery does work to drag it back to a high place and it kind of falls around the circuit. Okay, so that's pretty much what the battery does. Okay, so there's another little graphic, right? High energy, high potential at the positive side of the battery. The charges sort of fall around, give out energy to light the bulb, come back to the negative side of the battery, and now they're sort of at low energy, right? So then something has to be input, work has to be done to move that charge back to the top side of the battery. Okay, and that's the battery's job through the chemical reaction. Okay. Here's a couple of other little graphics that I kind of like. So you can think of the battery here as being like a pump, right? Pumping the charges to that high energy positive terminal, and then it will sort of flow down like water would in a pipe to a low energy. Okay. Back, the pump has to supply energy in to drag it up, and then it kind of falls back around. Okay. Same thing. I really like this little graphic. You can think of these little blue guys as being the charge. Okay, as we call here current, which we'll get into shortly. The charges, right, they sort of come into the battery to get their energy cup filled up, okay, as they climb to the top of the battery. And then they carry this energy around. They sort of dump out this energy cup at the battery to make light, and then they're empty. And then they come back around to the bottom side of the battery, the negative terminal, empty. The battery fills up their energy again, and then they sort of march around here, dump out the energy at the light bulb. Okay. All right. Another good graphic, right? There has to be a difference in this electric potential, so they say, right? So if there's a difference, say in a pipe, the water will flow. Same thing like the battery. The battery has to provide this potential difference, this voltage difference, right, in order to make it happen. If there's no battery, nothing's happening. There's no pump, there's no energy difference. Okay. So this thing that we're talking about, this so-called charge flow or current, it's not speed, and it's a little hard to talk about. And oftentimes we will say, oh, the current is faster. It's not faster. It means there are more charges able to get through. Okay, but it's really hard to conceptualize that, and I will slip up and say the wrong thing sometimes also. Okay, but basically the current is the amount of charge that can get through per time. Okay, and it's measured in what we call amperes, which is a symbol capital A. All right, it's not speed. It's actually very slow. Okay, so those electrons, or in conventional terms, what we say positive charges, are sort of bouncing all over the place here, like a person trying to make their way through a crowd, to get up to the, concert stage or something, right? It's not a direct path. The electrons sort of like bounce all over the place. So they sort of have what we call a drift velocity, which is very, very slow, about 1 meter an hour. Okay, so for the charges to get to the other side of the battery, to the other side of the circuit, even from your battery, is going to take like 15 minutes. Or something, right? It's very, very slow because they're sort of just bouncing all over the place, okay? A high current means there's a lot more of these charges that are doing the bouncing. That's what gives it a bigger charge flow overall, okay? The main thing to take away is that the charge actually moves very, very slowly. It's not fast at all, okay? All right, I think that was the last thing I wanted to show you. That was super unorganized, I think. I apologize for that, and we're not going to do that this year. So, okay, that is it. I hope that makes sense. If it does not, of course, reach out to your teacher. We are more than happy to help you.